Okay, so let's start with the second lecture. We're going to talk a little bit about convex sets and convex functions. And so, welcome back. I'll introduce an overview of convexity and duality, and then talk mainly about convexity and give you a summary at the end. So convexity is important because not all solvers, not all numerical solvers can guarantee to find the global minimum. So here on the left, you see a very complicated function. It's a two-dimensional function called the Rastrigan test function. It was designed to have lots of wiggles and lots of little local minimizers that you see the blue things at the bottom. And right in the center, there's one global minimum. But you can imagine that if you start an algorithm that follows the steepest descent, a gradient descent method from the outside, you probably won't get to the global minimum. And so this is an example of a non-convex function, and without convexity, many solvers only guarantee at best local optimality. In fact, maybe even only stationarity, which is a weaker concept. So convexity is important. Non-convex mixed integer nonlinear optimization problems are much, much harder to solve or guarantee solutions. You may not be able to prove global optimality. So even though you might find the global minimum, you might not have a guarantee that this is the best solution. And in some cases, you might want that guarantee. But it's also important to make sure that you really need non-convexity in your problem. So formulating problems in a convex way is safer, and sometimes there are reformulations. And I'll give you some in a later lecture, some of these reformulations. So we're back at our favorite optimization problem that has an objective function and nonlinear constraints. And so here's a little definition that says a feasible point is a point that is both integer. So notice that y hat is an integer point, and it's feasible if and only if it also satisfies the nonlinear constraints. So very straightforward definition. And then the feasible set of the mixed integer nonlinear optimization problem, if I had finished the bracket here, would be the set of all points that are continuous and integer that satisfy my constraints. Okay, so likewise, there's a definition of local and global minima. So a feasible point is a local minimum if there is a neighborhood around this point x hat, y hat, such that the objective function, if I evaluate it at my point, is less than or equal than the objective function at any other point that's feasible and inside my neighborhood. So the difference between local and global sort of can be illustrated in this picture. This point here is a local minimum because I can find a neighborhood. So on my x-axis here, I can find a neighborhood, an open set, for example, this set here. And if I evaluate my objective function in any point, then it's always greater or equal than the objective function there. But it's not a global minimum, because for a global minimum, it has to hold that it's the lowest objective function value for any feasible point. So this one over here, in this case, in a very simple example, that's my global minimum. And it's sort of important to note that we only do this for feasible points, because we might have a situation where we have some constraint. So here in this region, g of x and y is less than or equal to 0. Out here, g of x and y is positive, and I might have an objective function. I might have some contours, for example, So those are my contours of F. And so looking at it roughly, this would be my local minimum, but there's points where F has a lower value further out that are not feasible. So we're not looking at those feasible points, we're just looking at the lowest point in the feasible set. Okay, and you've seen all this before, and so convexity is really important. If we don't have convexity, then we might have potentially a lot of local minimizers, and it's not clear that what we find. So if you start a descent algorithm from any of these points that are further out, you're likely to converge to a point that's nearby. Not necessarily the nearest local minimum, but to a point that's likely nearby. It will be very hard to find the global minimum there. So convexity is defined as a set, this green set here, such that if you pick any 2 points that are inside the set, then the line that connects these 2 points also lies inside the set. So that's given up there. I take a point x0 and x1. This would be x0, there's x1. And then I take a convex combination. So theta is a parameter that's between 0 and 1. And then any of these convex combination is also an S. So if this is my x0, then as theta goes from 0 to 1, I move exactly along this line from theta equals 0 corresponds to x0, theta equals 1 corresponds to x1. So that's a convex set. A ball is a convex set. And here are 2 examples of convex and non-convex sets. A cricket ball to first order is a convex set. Really, if you think about the seams that are sticking out, that's probably not convex. Once it's been tampered with by the English bowlers, it probably also is no longer convex if they sneak things out. But the wicket is certainly non-convex. So that's an example of a non-convex set. I lived in the UK for about 12 years, and my wife was an avid cricket fan, so we watched cricket mostly on the television.
And cricket also has integer variables.
The wicket. Okay, and then, so there's the definition of a convex set there again. So convex set is a set such that pick any 2 points, the connection between the line between these 2 points lies in the convex set. And examples include the empty set. The empty set is convex because there's no point in it. Any convex combination of no points is no point. It's a convex. All of Rn, so the full space is convex because there's no boundary to it. A single point is always convex because the only way you form a convex combination is with itself. And a hyperplane is also convex. So if you have a straight line, you pick any 2 points along that line, then of course the straight line joining those 2 points lies inside your straight line. Likewise, half spaces, so A transpose X greater or equal to B, so that would be points where they lie on one side of a hyperplane, and I'm always going to shade the infeasible region as with these shaded things, so A transpose to X, here is greater or equal to B. That's again a convex set because if I take 2 points, x0 and x1, I join them up, they're always going to lie in the set. And you can try any combination of those that you like. This is interesting. A ball is a convex set. I think we established that earlier by example, but this holds for any norm. So for example, the 2 norm is your standard ball, your beach ball. The 1 norm is a diamond, and the infinity norm is a box. So they're all convex, provided, well, there's something there about the index of the norm. So any norm with, any p norm with p greater or equal to 1 is a convex set. The intersection of convex sets is also convex. So if I take the intersection of this convex set that I had here, and out there I have another convex set, then that would be this area here that I have over here, and that's again a convex set. Intersections of convex sets are convex. So you take an intersection of 2 circles, that's a convex set. But the union, and that's important, is not a convex set, and that's this example here. So if I take the union of 2 circles, then I get these 2 points. And I can choose 2 points here such that the line joining these 2 points does not lie in the set. So that's just a warning there. And then there's some useful definitions about convex combinations and the convex hull. And we'll talk about the convex hull more in terms of algorithms later. So if I take a number of m points that I have in Rn, then I form what's known as a convex combination. So I take multipliers lambda I that are non-negative and that sum up to 1. And I form this new vector, x lambda there. That's just the summation, the non-negative summation of these other points, xi. And the convex hull is defined as all the points that I can generate with any lambda that's non-negative. And so this plays a very important role in mixed integer linear optimization or integer linear optimization. So if I have these 4 points here, then the convex hull, a point in the convex hull is any point that corresponds to a non-negative linear combination of these 4 points, for example, here. And so the convex hull, another way of thinking about it is if I brought along some nails and a hammer, I could have nailed some nails into the board here, and the heads of the nails would correspond to these white dots. And then you take an elastic band and you release it around the nails. And so that's the convex hull of these points. So in R2, it's very easy to construct the convex hull because you just need a rubber band. In R3, you can probably do a 2 with a balloon that you deflate. But in higher dimensions, it's harder. And then there are some useful theorems. For example, the feasible set, a linear feasible set, is always convex. And it kind of follows from what we said earlier. The intersection of convex sets is convex. So I can just think of the feasible set of a linear feasible set as the intersection of all the hyperplanes, all the sort of half spaces xi greater or equal to 0, and then I have some affine constraints, and it's just the intersection of all of these. And because the intersection of convex sets is convex, this is convex. But you can also prove this directly. So what you need to prove for convexity is you pick 2 points inside your feasible set. So x0 and x1 are any 2 points that are inside my feasible set, and I pick a theta, an arbitrary theta between 0 and 1. And then it's very easy to see that the convex combination that I get here with any theta between 0 and 1, between x0 and x1, is non-negative because the original points are non-negative, x0 and x1 are non-negative, and theta and 1 minus theta are non-negative because theta is chosen between 0 and 1. So theta is greater or equal to 0 and less than or equal to 1. And then I do the same thing for the other constraints. So now what I've now shown is that my convex combination is non-negative. Now I go for the linear affine constraint, and so I just pre-multiply. I just put my new point, my convex combination, into my affine constraint, and then because it's a linear constraint, I can pull out the terms 1 minus theta and distribute my matrix or linear operator. And then because these 2 points are inside my feasible set, ax0 and ax1 are b and b respectively. And then I have a term theta b minus theta b and plus theta b that conveniently cancel, so I'm just left with b. So that means the point, if I have 2 points in my feasible set, then the convex combination is also in the feasible set. That's it. It's very simple. These proofs are very simple, which makes it nice to do them. Extreme points. Extreme points are also very important because they give us often good cutting planes, which we'll come to later. So they give us a way of algorithmically solving mixed integer nonlinear optimization problem. And an extreme point is a point such that I cannot express it as a convex combination of two other points in the set. That's what's written there in this definition. So X is in my set, is an extreme point. If for any other points, x0 and x1 that are in my set, I cannot express it as a convex combination of these 2 points with theta that's strictly between 0 and 1. And so here, for example, is a sort of image. The extreme point, there's 5 extreme points. Those are the corners here. Does anybody know what the extreme points are in this circular object? Sorry? There are infinitely many of them. Every point on the boundary is an extreme point. So extreme points are vertices of feasible sets. They cannot be written as strict convex combination, and they're very important for algorithms. So we're not going to talk about the simplex method for linear programming. That's an active set method that works, that solves linear optimization problems of a linear objective over an affine set by moving from one vertex to the next. And they're also very important in global optimization. Okay, and then the convex function is defined as saying, okay, I have a function f, so think of this green function here, and I just look at the epigraph, that's the set that's above my function, and I take any 2 points in this epigraph, I draw a line between them, and that's still in the, all the points along the line are still in the epigraph. So here I take 2 points, and I draw a line between them, and any point in that line is in the epigraph, or another way of saying that is that my function evaluated at any point at this convex combination, so there's a convex combination on the left-hand side, f of 1 minus theta, x0 plus theta x1, so any point that lies between these 2 extreme points, if I evaluate my function, then I'm on the green line, and that's less than or equal to the convex combination of these 2 function values here. So in other words, my function lies below the secant. So you can think of the red as a secant, and if you take a secant, then you have a convex function. If the function is convex, if for any secant, your function always lies below the secant. That's what this definition says there. Yeah? Okay, the previous one, yes.
So these extreme points, when we are defining extreme points, are we assuming that the set is convex set?
So the question was, if we're defining extreme points, are we assuming that the set is convex? Yes, we are. I think, yeah, they only make sense for convex sets, though I can think of extreme, well, that's a good question. I don't really know the answer, to be honest, but I think we are looking at it in terms of convexity. So let's make that assumption.
Yeah, because when we do not assume it is a convex set, then the extreme points, this combination would be possible. Like this set that you have.
Yeah, because there are points on the boundaries that are not extreme because they are convex combinations.
Okay.
In the middle of the curve, I think it's.
Yeah.
So that's not an extreme point by the definition because
Right.
it's a convex combination.
Yeah.
But yeah, I mean they're only useful. They only use extreme points in convex.
Yeah.
With convex sets.
Yeah. We only use
Yeah.
extreme points in convex settings, so we're not going to define them for other cases. I'm not sure if there is a generalization or whether it makes sense to do that. Okay, so we looked at the convex function. And so here's again, just again repeated the definition of a convex function. Sorry, this is a definition of a convex differentiable function now. So we say a function, the green function is convex, if and only if the function lies above the supporting hyperplane. So let's decode what's on the right-hand side there. On the right-hand side, we have taken a Taylor expansion of our function around the point x0. So here's x0, that's the point where we just touch. And the right-hand side is a first-order Taylor expansion of my nonlinear function around that point. So for any point x1, the function value lies above this supporting hyperplane. So the hyperplane touches the function. You can see that it touches the function at x1. So if you put x1 equal to x0, then the right-hand side, the gradient term vanishes, and you have x0 greater than or equal to x0. So it touches at x0, and at any other point, this hyperplane lies below the function. And examples of convex functions are linear functions are again convex, so that's nice. Quadratics with a positive definite Hessian. So the second order term has all positive eigenvalues. Norms, p norms for p greater or equal to 1 are convex. And convex combinations of convex functions. So if I have one convex function f1 and another one f2, and I take a convex combination of these with a parameter that's between 0 and 1, then that's again a convex function. So I can build up a mechanism, I can build up convex functions out of this. And then you can go further. You can also say a convex smooth function, so if it's twice continuously differentiable, then a function is convex if its Hessian is positive semi-definite. So positive semi-definite here means that all eigenvalues are non-negative. And so, for example, quadratics with a positive definite Hessian are convex functions. Positive semi-definite Hessian are convex functions. And then there's a sort of inverse of convexity, which is called concavity. So a function is concave if and only if its negative is convex. So this is the picture that you saw earlier, just turned upside down. So here is red is a concave function, it opens upwards, and what I've drawn here is a hyperplane that's now sitting above it, and the function, if I turn this upside down, then you have the definition of convexity again. So a concave function lies below any linear tangent plane, and the Hessian of a concave function is negative semi-definite, which means all its eigenvalues are less than or equal to 0. Okay. So we can now define what we mean by a convex programming problem. And so I'm doing this here only for continuous variables. And then I'll generalize it in a moment to our mixed integer nonlinear problem. So we say that for this nonlinear optimization problem, which just has continuous variables, where the functions f and there should be g are convex functions, you can show, there's a theorem that you can show that all local solutions, any local solution is also a global solution. So you no longer have the situation where you have multiple local minimizers, there's only one local minimum. And that holds also in the constraint set. And in fact, the set of these global solutions, which are also local solutions, is convex. So that's a very nice property. So this means that when you solve these problems, when you find a local minimizer, you know you have the global minimizer. Moreover, the solvers that we have, the nonlinear optimization solvers, all guarantee convergence to stationary points under quite reasonable assumptions. And in this case, stationary points are local minimizers. Local minimizers are global minimizers. So your nonlinear optimization solver guarantees to find a global solution under some additional assumptions, possibly. And so there are these first order necessary and sufficient conditions, which we'll talk about later. And for the minimum of a convex program, they're necessary and sufficient. So think of those as first order conditions. So if I have a convex function, the condition of having a minimum is that the gradient is equal to 0 for this function f of x. And in the constraint case, that's slightly more general. And there's an example, for example, where you can also have a flat bottom here. And now any point in this set is a local minimum or local minimizer, and that's a convex set. So that's sort of an illustration of what's going on there. So these problems, these mixed integer nonlinear problem, optimization problems, they sort of specialize, and Pietro will talk a little bit about the convexity of these problems. So I just wanted to sort of say what some of these problems could be like. So there's second order cone programs or optimization problems, mixed integer polynomial program if the functions are all polynomials. Very important role is mixed integer quadratic program, and with some abuse of notation, we say that this is convex if these functions, the Hessians, are positive semi-definite. So convex MIQP is a special case where the Hessian matrix, the Q, is positive semi-definite, and there's an X missing here after the PI transposed. And then mixed integer linear program or mixed integer linear optimization problems are problems where we have a linear objective and linear or affine constraints. So this is a slide that I took from Jeff Linderoth and a course that he and I taught at one point. And it's a tree of how optimization problems are kind of connected. It gives you an overview of some of the problems we're going to see in the course. So we're talking about min-low or min-LP, and there's a big dividing line here, this purple line. On the left-hand side, we have the non-convex world. On the right-hand side, we have the convex world. And so a non-convex problem, for example, a non-convex MINLP specializes to a non-convex NLP if there are no integer variables, or a mixed integer polynomial optimization problem if the functions are polynomials, and more general than, for example, a non-convex MIQP or a non-convex QP. And on the convex side, there are convex mixed integer nonlinear problems, convex NLPs, second order cone programming problems, and then they specialize to convex QP and finally LP. And as you go from the top to bottom, you're specializing the functions become simpler. So at the bottom here, you have linear functions. And as you go from the inside out, you're dropping integer variables. So this is sort of a convenient way of thinking about where these complexity class fit, or where these problems fit in, and that min-low or min-LP is a very, very broad modeling paradigm that covers all of these different classes of problems, and it's very, very generic. And often we make sure that we take advantage of special structures when we solve these problems. Okay, so here's a little bit of fun. And so you can ask Pietro interesting questions in the afternoon about complexity. So this is, Jeff coined this, the Leyffer, Linderoth, Lütke measure of complexity. And so this is a new class of complexity that supersedes P and NP and any other classes of complexity that you might have heard of. Given a problem in class X with Y decision variables, what is the largest value for Y, the number of decision variables, for which Jim, Jeff, or Sven would be willing to bet $50 that a state-of-the-art solver could solve the problem. So it's a very practical class. It says, you come to me, you have a problem class, you come to me, and I'm prepared to bet that we have a solver that can solve it with 5 problems or with 500 problems. And here's what we had about 5 or 6 years ago for this complexity class. I'm not sure if this is still accurate or not. So when you're convex, the world is really nice. So for the most generic problem that we had before on our little table, for a min-low, with 500 problems, we're pretty sure we can solve that. So I'm prepared to bet $50 that if you give me a convex min-low, I can solve it. I know I have high expectation of winning that bet. For nonlinear problems, 50,000 variables, I'm pretty sure we can solve that. That's, again, there's lots of solvers out there. For some of these second-order cone problems, it becomes a bit smaller. MIQP, mixed integer quadratic optimization problem, we're a bit more cocky. We give you twice as many variables if we want to bet. And then if you go larger for linear programs, 10 million variables, we think there are solvers out there that can manage it. There are also, I also know that you can give me a linear program with 10 million variables that I will not be able to solve, but at least in expectation, we believe we can win these bets. We don't like to lose bets. I don't know about you guys. We like to win these bets. So that's why this is sort of conservative a little bit. But on the non-convex side, this gets much, much harder. And so there are mixed integer nonlinear optimization problems where even with 100 variables, we may not be able to solve them. And so this is much, much harder. And it tells some story about this big divide between convex and non-convex that's happening. So convexity makes it much, much easier to solve problems. We can solve much larger instances than for non-convex problems. So convexity is kind of the great divide in optimization. If the world is convex, everything is easy. If it's non-convex, it becomes much more challenging. Unfortunately, a lot of applications are non-convex, and non-convexity really appears in many applications. In the power grid, when you're designing wind farms, non-convexity appears everywhere. And they're efficient and robust solvers for convex problems, but for non-convex problems, it's much, much harder. And then I had some examples of convex sets. So, in a ball is convex because any 2 points you join a line, it's convex. You have a convex function if you take a function that's a secant, and then the nonlinear function in between the two secant points lies below the function. And there's extreme points and convex halves. So that concludes my second lecture. And I apologize for running over time, but we'll make up for it later.
Questions? I have a short remark on that.
You have a short remark. Do you want to use a microphone or?
No. So that LLL is sort of a oblique reference to Lenstra and Lovash's algorithm for solving MILPs in polynomial time when the dimension is fixed.
Oh, okay. I did not know that.
So that's a very famous result in integer programming. So this result by Lenstra and Lovash, which says that if n is fixed, then you can solve an MILP in polynomial time. Otherwise, you take 2 to the power n or a to the power n steps. But if n is fixed, you can solve any MILP in polynomial time. So this is a nonlinear version of that very famous LLL.
But not as
result.
Not as precise or.
Of course.
Okay.
So what's the end here? What's the end in which you mentioned, right, if n is fixed? So what's the end here?
N is the number of variables.
N is the number of variables in that problem. So for a fixed number of variables, the complexity doesn't depend on n. It just depends on the encoding size, the number of constraints maybe. But there's the result then that says for fixed n, you can solve it in polynomial time.
So can we make it generic that QP is relatively easier with respect to MILP?
So the question was, can we make it easier that QPs are easier than MILP? Not, yeah. Not in the integer case. For convex problems, I think this is true. They're easier to solve than MILPs because they're continuous. And there are some classes of QPs which are very easy to solve. Like if you only have equality constraints, so if you have a very specific QP, I'm going to write this here on the board. Half x transpose gx plus p transpose x subject to ax equals b, then this is a very easy problem. And you can solve very, very large instances of this problem.
X can be, there are no inequalities.
Correct. There are no inequalities. And if G is convex, I should have said, and you can relax convexity, then what you need to do is the first order conditions become a system of equations that basically has something like, maybe I should be careful and write this down, but it's a system of first order conditions that's a 2x2 system involving the matrix G and matrices A and A transposed. And so it's a 2x2 block system, and there's very efficient methods for solving this problem. And this arises, for example, in PDE constraint optimization, where AX equals B is the discretization of a partial differential equation. And so you can go up to billions of variables in that case, using then iterative solvers to solve these systems. But we're not going to go that big here. Okay.